So alright, let's finish the proof of the main theorem, and I'm sorry if video 2 was really technical, really topology stuff. Here I will focus more on some geometry arguments, and this is my favorite part of the proof by far. So let's do it. Okay, the t-parallel surfaces. Let's analyze these surfaces, how they behave, what are their properties. First, here's again the lemma which will give us the properties we need for the t-parallel surfaces. So let n be a hyperbolic trimanifold of finite volume and sigma a proper two-sided totally geodesic non-separating surface with distinct ends of sigma embedded in disjoint ends of n. In other words, let sigma be something created with the properties as the previous theorem. So you take the t-parallel surfaces to it, you go exponentially by a fixed distance, and the properties that this surface sigma t has is: first, it has constant mean curvature equals to hyperbolic tangent of t, which is a number in between 0 and 1, and 1 t goes to infinity, this number goes to 1. The second, they are all properly immersed, and this could be false. I mean, I wouldn't expect this to happen because we are in a manifold of finite volume, right? So you don't have space to go. So you could go parallel and then you start accumulating. So this wasn't clear, but you see that it's actually simple to show that this happens. It's impressive actually. So every t-parallel surface is properly immersed, and moreover, this is amazing, there exists a small value of t such that they are actually properly embedded until that value. So let me present the proof of this lemma, and we focus on the non-compact case because if n is compact, everything is trivial. And let me give you the proof of this lemma. Okay, so let sigma be as stated. So here I am picturing it like this. It's not correct because this sigma seems to separate your ambient, but our sigma actually does not separate the ambient space, but it's alright. So let sigma be as stated, and the thing is, we go parallel to it, and we know that it has constant mean curvature equals to this number because that's what happens in hyperbolic tree space when you have a totally geodesic surface. But now, how do we prove that this is well behaved? We need to look at the ends of this surface. We need to look at how the ends of sigma t behave, because everything which are in this part of the manifold, in the thick part, is in a compact part, so we know it's well behaved enough, at least for small values of t. So the ends of sigma go like this. The end of sigma is basically this vertical plane. It's a geodesic of the torus times r, and we can orient it with any normal unitary vector field we would like. And what happens is that you take the universal covering of the end by a horoball of H3, as I described in the first video, and this totally geodesic surface actually comes from a totally geodesic surface inside this horoball. So it's if this is the half space model of H3, this is just a vertical plane. Remember, this has the topology of S1 times R, and this has the topology of R times R. We are quotienting by one translation, like in the direction of the video. So, okay, so we have here our totally geodesic example, which is mapped by the universal covering of the end in your end of sigma. And what happens is that the exponential map go like this by orbits of geodesics in H3, which are by circles. So when you go parallel in H3, you are just going to a tilted plane. This is just a tilted plane. And this tilted plane goes here by the universal covariant transformation as a tilted plane, basically. So it has constant angle with all this foliation by tori. In particular, it never intersects itself. I'll say it again. You have this totally geodesic surface in a space with no space at all, really small volume, and then you go parallel and it never intersects itself. In the ends, it intersects the original surface infinitely many often, but it never intersects itself. You can make the computation here to see that is explicit. It never intersects itself. This is magic. It's plain magic. I'm impressed until nowadays that this is true, but it's fantastic. So the ends are properly embedded. They don't accumulate, they don't intersect themselves. For any value of t, the ends are properly embedded. This is a great property. So if the ends are properly embedded, what's left is compact, so sigma t is properly immersed. Really not much to do here. So in the thick part, more than properly immersed, we have a regular neighborhood. So for small values of t, we know that this part in the thick part is properly embedded. And it's just a simple argument to show that if this is properly embedded and what's in the ends is also properly embedded, we can make them don't intersect. We can show that they do not intersect. There is nothing on the thick part going inside the thin part, and there is nothing on the thin part going outside to the thick part. So they are properly embedded for small values of t. This proves the lemma. So we now have in our outline of the proof everything until this point. We have a totally geodesic example with the topology that we want, and we use this totally geodesic example to find t-parallel surfaces to it, which are all properly immersed, and for small values of t, they are properly embedded. So the theorem would be proved if we didn't ask for embedding still. So now the last part we want to do is to produce properly embedded examples for any value of h that we want. So let's do this. Fix your value of h, fix your topology, you take your totally geodesic example as given before, and we work with this example. So you have a totally geodesic example in a hyperbolic trimanifold of finite volume n. We take the t-parallel surfaces and you find your value of t naught, which is defined by this equation. Since h is 0, 1, t naught exists. Now, we take the supremum value such that the t-parallel surfaces are still embedded, and we assume that this t naught is bigger or equal to this supremum, because if t naught was less than t, then sigma t naught would be embedded, and we have reached this value of the mean curvature. So we have to assume that t naught is bigger or equal to t. So what happens with sigma capital T? First thing, it's not embedded. Being embedded, it's not a closed relation. We have a sequence of embedded surfaces converging to something which is not embedded. And moreover, there exists a closed geodesic in n, and we know the length of this closed geodesic. This property is something that actually allows us to do to continue our proof. Let me explain you how we find this closed geodesic. It's quite simple. We are here on the thick part because we know that the thin part is always embedded. In the thin part, sigma t is always embedded. So you have your totally geodesic surface here, and you have the normal exponential map, and we know that we have embedded surfaces sigma t converging to something not embedded. So we have a first point of contact. And this contact has to be tangential, and this is really important. So this point comes from the normal map over a certain point in sigma, and this other point comes from a different point in sigma. But this was a normal exponential map, so this is a geodesic. There is a geodesic joining this point and this tangential point, and it is perpendicular to sigma, and also there is another geodesic arc here joining this other point to this point. So actually this arc is smooth because the intersection here is tangential, and this is perpendicular to sigma, this is perpendicular to sigma. Remember that sigma is in the fixed point set of an order 2 isometry of the ambient space, so you can flip. You can use this reflection and reflect this geodesic arc here and form a closed geodesic. And since we know the distance, we know that this distance is t, this distance is also t, so this length here is 2 times t. So here you have your closed geodesic of length 4 times t. Okay, how do we use this closed geodesic here? Let's give some recapitulation here. You have a proper embedding with image sigma, which is totally geodesic in the fixed point set of an order 2 isometry. We know that the parallel surfaces are embedded in this range, but in the boundary of the range they are sigma capital T is not embedded, and this generated a closed geodesic with length 4 times t. Now we take L equals 5 times t naught, and we know that 5 is bigger than 4. That's the only reason we chose 5. It could be 4.1, 4.00001, anything larger than 4. And we know that t naught is larger or equal to t. So L is strictly larger than 4 times capital T. Okay, now we consider the finite set. Actually, we consider the set. Let's forget finite for a while. We consider the set of closed geodesics which has a length less than this number L and meet sigma orthogonally at some point. And since they meet sigma orthogonally at some point, they must be invariant under reflection by the uniqueness of geodesics, right? So the thing is that this set is finite. If you take the closed geodesic up to congruence, right? If you take the set of closed geodesics with a bounded length in a hyperbolic trimanifold of finite volume, this set is always gonna be finite. Okay, so what's the idea here? We need to remove these geodesics, because if you don't have geodesics with lengths less than L, you can go a little further on with your embedded T-parallel surfaces. That's the whole idea. We need to remove these geodesics from N. Obviously, we cannot just remove a geodesic from a manifold, but the idea here is to build a finite cover from a different manifold to your original manifold, such that the totally geodesic surface lifts, and so you have another embedding into N tilde, and no small multiple of gamma I of all these geodesics here lifts. So this space here will not have closed geodesics with lengths less than L which meet sigma or sigma tilde orthogonally at some point. And I forgot to write it down, but we also want that the isometry to lift. I forgot to write that down, but I'm saying it here. Okay, the consequence from this, if we can find this finite covering, is, as I said before, we have a totally geodesic surface in your new hyperbolic trimanifold of finite volume, because this was a finite cover, so the volume of n tilde is just a finite multiple of the volume of n. So we have a totally geodesic surface in that other manifold. It's in the fixed point set of an order 2 isometry, which is the lift of this order 2 isometry. It won't separate. It will have all the good properties that we need. So we know that the T-parallel surfaces are going to be embedded at least for this value of H, which is larger than T naught. So the surface sigma tilde T naught will be properly embedded in your manifold, and will be an example as we wanted. So this is the idea for the proof, and let's show you how to build this finite cover. First, really quickly, let me address how you build covers at all. Like, the main idea here is each covering space is related with a subgroup of the fundamental group of your ambient space. So if H is any subgroup of pi 1 of n, there exists a covering from nh to n such that the push forward of pi 1 of nh is exactly that subgroup H. And more importantly, the index of H in pi 1 of n is equal to the number of sheets of pi. In other words, if the index of H in pi 1 is finite, the cover will be finite. That's the idea to build finite coverings. And also we can remember that a function lifts to this covering space if and only if the push forward of pi 1 of x is in this push forward of pi 1 of nh, which is h. So that's what we want to do. We want to find a subgroup of finite index, really specific, so that sigma lifts, the isometry also lifts, but no small multiple of gamma I lift. So that's the idea. How do we do that? And this is something really, really interesting. I had a lot of fun learning this, because the fundamental group of hyperbolic trimanifolds of finite volume have a key property which was proven recently, that it is LURF. I just love saying LURF. LURF sounds like something interesting, right? LURF. And this was proven by the work of several people. I cannot write the names of them all, but they have work of Agel, Wise, and they are summarized in a book by Aschenbrenner, Friedel, and Wilton. I'm sorry if I didn't say the names correctly, but here is the definition of LURF. What LURF means. LURF stands for locally extendable residually finite, and the definition for it is: a group G is called LURF if for any finitely generated subgroup of G and for any finite set disjoint from this subgroup. So we have a finitely generated subgroup, and we have something, a set, which is finite and doesn't intersect the subgroup. And the idea is that you can separate these points, this set, from the subgroup in the so-called profinite topology. And in practical terms, this means that there exists a representation from G to a finite group, and this is important, F is a finite group, such that the image of these elements is disjoint from the image of H. That's the definition of LURF, and we are actually gonna use it. It's I think I am overselling it, but this is really cool. I really had a lot of fun using lerfness. I love this word. I love this property, and it actually is useful. Okay, let me explain how we use lerfness. I think I am blabbering too much. How to use lerfness of pi1 of n to construct a finite cover of n with the properties that we want. First, we need a lerf group, which is pi1 of n. Then we need a finitely generated subgroup, which will be pi1 of sigma. You take the fundamental group of, actually you take the push forward of the fundamental group of your topological surface as your original surface, and since S has finite topology, H is finitely generated. I am omitting base points. I forgot to mention that before, but I am forgetting about base points. Everything here you need to choose base points, but I think it just complicates the notation and it doesn't add any insight on the proof, so I'm not talking about base points here. Okay, so you have a lerf group and you have a finitely generated subgroup. Now you need a finite set. And the finite set disjoint from H will be the set of the closed geodesics of length less than L, which meet sigma orthogonally at some point. So the representatives of this closed geodesics in pi1 of n actually. And it's easy to prove that this is disjoint from n because they are geodesics orthogonal to sigma. Sigma is totally geodesic, and it's just a simple argument to show that they are actually disjoint. Oh yeah, and I am counting them with multiplicities. In other words, gamma 2 could be gamma 1 wrapped around twice. If gamma 1 has like a tiny length, gamma 2, when you go gamma 1 twice, you could still be small, so I am counting everything here with multiplicities as long as they have lengths less than the big L we defined previously. Okay, so we can use lerfness to separate this set from this group, and you find a representation sigma from pi1 of n to f, where f is a finite group, and we know that the images are disjoint. Okay, now how do we use this representation here? Remember, we need to find a finite index subgroup of pi1 of n. So we could, for instance, take the kernel of this representation, because f is a finite group. So the kernel would have finite index here in pi1 of n. But the problem is, if we just take the kernel, this property is killed. We cannot use this property if we take the kernel. So we need a little more than the kernel. We let h1 be the inverse image of the image of h. So this is basically h together with the kernel, and we take a finite index subgroup which contains both of them. Basically that's it. Now we make the intersection of this subgroup with the reflection of this subgroup by the isometry. What happens is that h is contained in h2 because obviously h is contained in h1, but also h is invariant under phi star. So h is contained in h2, and this is going to be really important. But then the kernel of sigma has to be contained in h1 because you were taking a pre-image of a subgroup. So h1 has finite index in pi1 of n. But since h2 is the intersection of h1 with phi star of h1, which also will have finite index, h2 has finite index in pi1 of n. And this is the group we will use to construct our covariant transformation. We take this Riemannian covering such that pi star of pi1 of n tilde is exactly h2. And this is all we need, because first, pi is a finite covering because H2 has finite index. So n tilde is a Riemannian hyperbolic trimanifold of finite volume. Okay, moreover, f star of pi 1 of sigma is exactly h, and h is contained in H2. So f lifts, and we find a totally geodesic surface in n tilde, properly embedded with all the properties and with the topology S that we wanted to start with. So finally, phi star of pi 1 of n tilde is also contained in H2, because pi star of pi 1 of n is H1, actually is H2, and H2 is invariant under reflection. So this is contained in H2. So this map here, the composition of phi and pi, lifts to an order 2 isometry of n tilde. And that creates our surface, our totally geodesic surface, with the properties that we already know that we need. And finally, since gamma I is not in H1, and H1 contains H2, so gamma I is not in H2, and these geodesics don't lift. And that's what you need to create your finite cover, such that you have a totally geodesic surface there without any closed geodesics intersecting it with length less than 5 times T naught. And as explained previously, this proves the theorem. So that's it. Thank you very much. I hope you enjoyed the talk. And if you have any questions, please do submit them online. I know we will have a Q&A section soon, so ask your questions, and if I can, I will answer them. So thanks again for the organizers for the invitation, especially to Hojo, and see you next time.